Welcome to our deep dive. We're going to be exploring the wonderful world of elements.
Oh, that's a great topic.
And our guide for this journey is Sam Kean's book, The Disappearing Spoon. It's packed with fascinating stories about the elements from, the history of their discovery to the lives of some pretty quirky scientists.
Oh, I love that book. It's so engaging. Kean really brings the elements to life.
Right. And we'll also be uncovering those surprising ways that elements pop up in our everyday lives, like in medicine, technology, even warfare.
It really is amazing how these tiny building blocks, the elements, influence every aspect of our world.
Yeah, and we're going to uncover all of that more in this deep dive. So let's start with the basics, the periodic table itself. Now, I know it can seem a bit intimidating at first glance,
Yeah, all those symbols and numbers.
but it's actually brilliantly organized. Could you maybe break it down for us a bit?
Absolutely. So the arrangement of elements on the periodic table is based on their atomic number. That's the number of protons in an atom's nucleus. And as you move across the table from left to right, the atomic number increases.
Okay, so that's how it's organized. But how does that arrangement tell us anything about how the elements behave?
Well, the rows and columns, we call them periods, and groups, group elements with similar properties together. And that's what makes the periodic table so powerful. It allows us to predict how elements might interact with each other based on their position on the table.
So the table's structure actually reflects those underlying patterns in how elements behave.
Exactly. It's like a map that guides us through the world of chemistry.
Okay, that makes sense. Now, I remember Kean talked about the noble gases and how they're sort of like the loners of the periodic table. They occupy that far right column and are notoriously unreactive.
Right. They're the introverts of the element world.
So why are they so aloof?
Well, it all comes down to their electron configuration. They have a full outer shell of electrons, which makes them very stable. They don't need to gain or lose electrons to achieve stability, so they don't readily form bonds with other atoms.
So it's like they're content with their own company.
Exactly. Helium, the second element on the table, is a great example of this noble gas behavior. It was actually discovered in the sun's atmosphere before it was found here on Earth.
Really? In the sun first? That's pretty wild.
It is, and it highlights the importance of spectroscopy, a technique that allows us to analyze the light emitted by different elements.
Okay, spectroscopy. So that's how we can study the composition of stars from millions of miles away.
Precisely. By analyzing the light from a star, we can identify the elements present in its atmosphere. It's like taking a fingerprint of a star's chemical makeup.
Wow, that's amazing. And speaking of helium, I remember Kean mentioned something called helium superfluidity. It sounded a bit like something out of a comic book.
It does sound pretty fantastical, but it's a real phenomenon. When helium is cooled down to extremely low temperatures, close to absolute zero, it exhibits some incredibly strange behavior.
Oh.
It can flow without any resistance, climb up walls, and even escape from sealed containers.
No way. That's crazy. How is that even possible?
Well, it's a consequence of quantum mechanics, those bizarre rules that govern the behavior of matter at the atomic and subatomic levels. At such low temperatures, the individual helium atoms lose their individual identities and behave like a single, unified wave.
Okay, that's definitely a mind bender.
It is. And it's just one example of the many bizarre and beautiful phenomena that we encounter when we delve into the world of elements.
Now, I know we've talked a lot about these broader groups of elements, but Kean also tells some fascinating stories about individual elements. For example, he talks about antimony and its role in creating superacids.
Oh, yes. Superacids. They're some of the strongest acids known to science.
And when we say strong, we're not talking about the stuff you use to clean your drain.
No, definitely not. Superacids are millions, sometimes even billions, of times stronger than conventional acids. They can dissolve things that would laugh at normal acids, like glass and even some metals.
Eat through glass. You definitely wouldn't want to get any of that on your skin.
Absolutely not. It would be extremely dangerous.
So where do we even find these superacids? Are they just lurking out in nature, waiting to dissolve unsuspecting hikers?
Thankfully, no. They're typically created in laboratories by mixing very specific combinations of chemicals. One example is a superacid called fluoroantimonic acid. It's made by mixing antimony pentafluoride with hydrofluoric acid, both of which are already pretty nasty on their own.
So it's like a recipe for chemical chaos.
Pretty much.
Mm-hmm.
But even though superacids are incredibly dangerous, they also have some important applications in chemistry research and industry. They can be used to catalyze reactions, create new materials, and even help us understand the fundamental nature of matter.
So another example of how the elements can be both destructive and incredibly useful depending on how we handle them.
Exactly. And it highlights the importance of understanding the properties of elements so we can use them safely and effectively.
Now, we've talked about superacids, but Kean also delves into the work of Maria Goeppert-Mayer, a physicist who made groundbreaking discoveries about atomic nuclei. I have to admit, nuclear physics isn't exactly my forte, but Kean does a great job of explaining it in a way that's easy to understand.
Goeppert-Mayer's work was revolutionary. She discovered that the nuclei of atoms are structured in shells, similar to the way electrons orbit the nucleus, and she found that certain nuclei, called magic nuclei, have completely filled shells, making them very stable.
Okay, so we're seeing that theme of full shells and stability again, like with the noble gases.
Exactly. It's a recurring pattern in the world of elements.
And this concept of magic nuclei connects to things like why we need oxygen to breathe and why certain elements are so abundant in the universe.
It does. For example, oxygen has 8 protons and 8 neutrons, making it doubly magic with full shells of both. That stability is one of the reasons why oxygen is so plentiful and so crucial to life as we know it.
Wow, so these seemingly abstract concepts in nuclear physics actually have profound implications for the very existence of life.
They do. It's all interconnected. And that's one of the things that makes the study of elements so fascinating. It touches on every aspect of our world and beyond.
Absolutely. Now, Kean also delves into this really unique aspect of the periodic table. The longest word in the English language. It's a massive string of syllables that describes a protein found in a virus.
Oh, yes. That was a fun one. I remember trying to pronounce it, but it's a real tongue twister.
I can imagine. But what's the connection to the periodic table?
Well, this incredibly long word is essentially a chain of amino acids linked together. And amino acids, which are the building blocks of proteins, all have a carbon backbone. So this crazy long word is a testament to carbon's unique ability to form long chains and complex structures.
So carbon's versatility is reflected not just in chemistry, but even in language.
Exactly. It's the element of complexity, both in the natural world and in our attempts to describe it.
And that brings us to the question, could life exist based on an element other than carbon? Kean explores the possibility of silicon-based life. Silicon sits right below carbon on the periodic table and shares some similarities in how it bonds with other elements.
Right. It's been a popular theme in science fiction for decades.
Are we talking about silicon-based aliens somewhere out there in the universe?
Well, while silicon can form bonds like carbon, it's not as flexible or versatile. For example, silicon struggles to form the complex ringed structures that are so common in organic molecules.
So silicon-based life might not be as complex as carbon-based life.
It's a possibility. Silicon also has trouble forming double bonds, which are crucial for many biological processes. So for now, carbon still reigns supreme as the foundation of life, at least as we understand it.
It's fascinating that the periodic table gives us these hints about the possibilities and limitations of life itself.
It really is. It's like a roadmap to understanding the fundamental building blocks of the universe and the incredible diversity of life that can arise from them.
Absolutely. Now, let's bring the conversation back to Earth and the history of element discoveries. Kean tells the story of germanium and its brief moment in the technological spotlight.
Ah, germanium. It played a key role in the early days of transistors.
Transistors, those tiny electronic components that revolutionized technology.
Exactly. Germanium was one of the first materials used to create transistors. It was a big deal for a while.
But then it didn't last, right? What happened?
Well, silicon ultimately proved to be more practical and abundant for creating transistors. Silicon could withstand higher temperatures, which was crucial for making more powerful electronic devices. So germanium, despite its early promise, was eventually overshadowed by silicon.
It's like the Betamax of elements. It paved the way, but was ultimately outdone.
That's a great analogy. And it's just one of many stories of technological innovation and competition that we find in the world of elements.
It makes you wonder how many other elements are just waiting for their moment in the spotlight, their unique properties waiting to be harnessed for some new and groundbreaking technology.
Absolutely. The possibilities are endless.
Speaking of fascinating stories, Kean also introduces us to some pretty colorful scientists. Robert Bunsen, the inventor of the Bunsen burner, sounds like quite a character.
He was a brilliant scientist, but also a bit of a daredevil. He had a near-fatal arsenic accident.
Wait, what? Did he just spill some arsenic on his lab coat?
It was much more dramatic than that. An entire beaker of arsenic exploded in his lab, nearly blinding him. But that didn't deter him from continuing his scientific pursuits.
Wow, the man was clearly dedicated to his work. What other adventures did he have?
Well, he was incredibly passionate about volcanoes. He even built a replica of Old Faithful in his lab.
He sounds like he was a lot of fun to be around.
He was, but his most important contribution to science was probably the spectroscope. It's an instrument that analyzes the light emitted by different elements, kind of like a fingerprint. It was a revolutionary tool that allowed scientists to identify new elements and study the composition of stars and other celestial objects.
So it's thanks to Bunsen and his spectroscope that we can analyze the light from distant stars and figure out what they're made of.
Exactly. His work opened up a whole new realm of scientific exploration.
That's pretty incredible. It seems like we've only just begun to scratch the surface of these elements and their stories. So where do we go next on this journey?
Well, there are some incredible stories about how element discoveries have been intertwined with politics and even warfare. For example, the discovery of gallium sparked a debate about the roles of theory and experiment in science.
Okay, now that sounds intriguing. Let's dive into that.
It all started with Dmitri Mendeleev, the creator of the periodic table.
Okay, Mendeleev, the periodic table guy, I remember him from chemistry class.
He was a visionary. He predicted the existence of an element he called aluminum, based on gaps in his periodic table, years before it was actually discovered.
So he basically looked at his table and said, hey, there should be an element here even though we haven't found it yet.
Exactly.
Mm.
And a few years later, a French chemist named Paul-Émile Lecoq de Baudouin discovered gallium, which matched Mendeleev's predictions almost perfectly.
That's like predicting the winner of a sporting event years in advance.
It is. And it solidified Mendeleev's reputation as a scientific genius.
So did Mendeleev's theory guide de Baudouin to the discovery of gallium?
That's the heart of the debate. Some argue that Mendeleev's theoretical framework helped scientists recognize gallium when they found it. Others say that the experimental discovery of gallium simply validated Mendeleev's table. It's a bit of a chicken and egg question.
A classic scientific debate. But beyond proving Mendeleev right, what's so special about gallium anyway?
Well, it has this really low melting point. You can actually melt gallium in your hand.
Really? That's crazy. I can imagine that would make for some pretty cool science demonstrations.
Oh, definitely. It's often used in pranks and science magic tricks.
Speaking of interesting places, Kean talks about this little town in Sweden called Ytterby that's given its name to no less than 4 elements.
Ytterby is like a periodic table gold mine. It's this tiny little town, but it's played an outsized role in the history of element discoveries.
4 elements from one small town. That's unbelievable. How is that even possible?
It's a combination of geology and scientific curiosity. Ytterby sits on a deposit of really unusual minerals packed with rare earth elements. And during the 18th and 19th centuries, Swedish scientists were at the forefront of element discovery. They were really good at isolating and identifying new elements.
So it was like this perfect storm of factors that led to all those discoveries.
Exactly. The right elements, the right people, and the right time.
It just goes to show sometimes the most incredible scientific discoveries are waiting in the most unexpected places. You never know where the next breakthrough might come from.
That's the beauty of science. There's always something new to discover, some hidden connection waiting to be made.
And we're going to keep uncovering those connections as we continue our deep dive into the wonderful world of elements.
I'm excited to see what else we find. There really is. And some of those discoveries take us far beyond Earth. Kean also explores this fascinating world of astrophysics, how elements are forged in the hearts of stars.
Oh, I love that part. It's always blown my mind how stars can create elements. It feels almost alchemical.
It does have a certain magical quality to it, but it's actually a pretty straightforward process, at least in principle.
Okay, so break it down for me. How do stars actually make elements?
Well, it all starts with hydrogen, the most abundant element in the universe.
Okay, hydrogen, the simplest element.
Right, just one proton and one electron.
And how do you go from hydrogen to, well, everything else?
Through nuclear fusion. In the intense heat and pressure at the core of a star, hydrogen atoms are forced to fuse together, forming helium and releasing a tremendous amount of energy.
Okay, so hydrogen fuses into helium, and that's what makes stars shine.
Exactly. And it's this fusion process that powers stars and creates all the elements heavier than hydrogen.
But how do you get from helium to things like carbon, oxygen, iron, all those heavier elements?
Through further fusion reactions. As the star ages, it starts to run low on hydrogen in its core. And when that happens, the core contracts, and the temperature and pressure increase even more.
So it's like the star is squeezing itself tighter and tighter.
Exactly. And at these higher temperatures and pressures, helium atoms can start to fuse together, forming heavier elements like carbon and oxygen.
And this process keeps going, creating heavier and heavier elements.
It does, but there's a limit. Stars can only fuse elements up to iron.
Iron. Why iron? What's so special about iron?
Iron is the most stable element in terms of nuclear binding energy. So to fuse elements heavier than iron actually requires energy rather than releasing it.
So it's like iron is the end of the line for stellar fusion.
Exactly. Once a star has a core made mostly of iron, it's reached the end of its life.
So what happens then? Does the star just fade away?
Not exactly. For massive stars, the end comes in a much more dramatic fashion.
Uh.
A supernova.
Oh, supernovae, those incredibly bright explosions that we can sometimes see from Earth.
Right. When a massive star runs out of fuel, it can no longer support its own weight, and its core collapses in on itself.
And that triggers a supernova.
Exactly. The collapse releases an incredible amount of energy, blasting the star's outer layers into space.
And it's during these supernova explosions that those heavier elements, the ones beyond iron, are created.
Precisely. The intense energy of the supernova is enough to force atoms together, creating elements heavier than iron, including gold, uranium, and all those other elements that make up our world.
So those elements were forged in these cataclysmic events, the death throes of stars.
It's a pretty amazing thought, isn't it?
Yeah.
We're literally made of stardust.
It makes you appreciate the interconnectedness of everything in the universe.
It really does. Every atom in our bodies was once part of a star, created in these incredible cosmic events.
And that brings us back to the periodic table. It's not just a chart. It's a storybook, a cosmic history of the universe.
I love that analogy. It really captures the essence of what the periodic table represents.
It's like a map that shows us where all these elements came from and how they're all connected.
Exactly. And it helps us understand the processes that have shaped the universe and everything in it, from the smallest atoms to the largest stars and galaxies.
Okay, now let's shift gears a bit and talk about how these elements have influenced the course of history. Kean doesn't shy away from exploring some of the darker chapters where elements have been weaponized. For example, he talks about Fritz Haber, the German chemist who played a complex and controversial role during World War I.
Ah, Haber. A brilliant scientist, but also a tragic figure. He's considered the father of chemical warfare, largely due to his development of chlorine gas as a weapon.
Chlorine gas, wasn't that one of the first chemical weapons used in modern warfare?
It was, and it had devastating effects.
Yeah, I remember reading about the horrific accounts of soldiers choking to death in the trenches.
It was truly horrific. Haber's work highlights the duality of science, its potential for both good and evil.
He was also involved in the development of fertilizers, right?
He was. His work on nitrogen fixation, which is essential for creating fertilizers, helped to increase crop yields and feed millions of people. But his legacy is forever tainted by his role in chemical warfare.
It's a reminder that even with the best intentions, scientific discoveries can be used for terrible purposes.
Absolutely. It's a lesson we must never forget.
And it gets even more tragic. There's a connection between Haber's work and the horrors of the Holocaust.
Yes, there's a chilling link.
Yeah.
Zyklon B, the deadly gas used in Nazi extermination camps, was a modified version of a pesticide that Haber had developed before the war.
It's a stark reminder that scientific progress doesn't always equate to moral progress.
It's a sobering thought. We must be vigilant in ensuring that science is used for good, not for harm.
Now, moving beyond the battlefields of World War I, Kean talks about other elements that have played significant roles in warfare, particularly during World War II. Molybdenum and tungsten, for example, were highly sought after for their use in steelmaking.
Right. Molybdenum and tungsten are both incredibly strong and heat-resistant metals, perfect for making weapons and armor.
So they were essentially strategic materials, crucial to the war effort.
Exactly. And there was even a controversy involving Portugal and its supply of tungsten to Nazi Germany.
I vaguely remember reading about that. Wasn't Portugal officially neutral during the war?
They were, but they also had a long-standing trade relationship with Germany, and they continued to supply tungsten even after the war broke out.
So neutrality was a bit more complicated back then.
It often is, especially when there's a lot of money to be made.
Okay, so Portugal was selling tungsten to Nazi Germany, even though they were supposed to be neutral. What was the big deal about tungsten anyway?
Tungsten was essential for making armor-piercing shells. It was also used in the nozzles of rocket engines.
So it was a key material for both offensive and defensive weaponry.
Exactly. And Portugal's tungsten exports likely helped to prolong the war.
Wow. It's incredible how the fate of nations can sometimes hinge on the availability of certain elements.
It is, and it shows how the periodic table, this seemingly abstract chart of elements, is actually deeply intertwined with the course of human history.
Absolutely. Now, speaking of influential figures, Kean discusses a physicist named Henry Moseley whose work had a profound impact on our understanding of the elements.
Moseley's work was truly groundbreaking. He was the one who figured out that an element's atomic number is the key to its identity.
Atomic number. Remind me again what that is.
It's the number of protons in an atom's nucleus. Prior to Moseley's work, the periodic table was arranged by atomic weight, which caused some inconsistencies.
So Moseley realized that atomic number, not atomic weight, was the defining characteristic of an element.
Exactly. And his discovery led to a much more accurate and consistent arrangement of the periodic table, the one we use today.
So he basically redefined how we understand the fundamental building blocks of matter.
He did. His work had a huge impact on the field of chemistry and physics. Sadly, though, his promising career was cut short. He was killed in action during World War I.
It's a reminder of the incredible human cost of war and the potential brilliance that can be lost in conflict.
It's a tragedy. And many believe that if Moseley had lived, his work could have led to even greater discoveries.
Now, speaking of World War II, Kean delves into the Manhattan Project and the race to build the atomic bomb.
The Manhattan Project was a massive undertaking, a top-secret effort to harness the power of the atom for military purposes.
And at the heart of this project was the challenge of understanding and controlling nuclear fission.
Right. Nuclear fission is the process of splitting an atom's nucleus, releasing a tremendous amount of energy.
And the key to achieving a controlled nuclear fission reaction was figuring out how much material you needed to create a critical mass.
Exactly. Too little material, and the reaction wouldn't sustain itself. Too much material, and you risk a runaway reaction, a nuclear explosion.
So they had to find that sweet spot, that precise amount of material needed to achieve a sustained chain reaction.
And to figure that out, they turned to a new and powerful tool, the Monte Carlo method.
The Monte Carlo method, that sounds more like something you'd use in a casino.
It does, but it's actually a powerful mathematical technique for solving complex problems using random sampling and probability.
So how did they use randomness to figure out how much material they needed for an atomic bomb?
Well, they created computer simulations that modeled the behavior of neutrons in a nuclear reactor. And they used random numbers to represent the different possible paths that neutrons could take.
And by running these simulations thousands of times with different random inputs, they were able to get a statistical picture of how the reaction would proceed.
Exactly. They could see how likely it was for neutrons to collide with other atoms and cause fission, and they could use that information to estimate the critical mass.
So randomness, when applied strategically, can actually be a powerful tool for solving complex problems.
It can. The Monte Carlo method is still used today in a wide range of fields, from finance to climate modeling to drug discovery.
So it's a technique that was born out of the urgency of wartime research, but has had a lasting impact on science and technology.
Absolutely. It's a testament to human ingenuity and our ability to find creative solutions to seemingly intractable problems.
Now, Kean doesn't shy away from exploring the darker side of nuclear technology. He talks about the concept of a cobalt-60 dirty bomb.
A dirty bomb is a truly terrifying weapon. It's essentially a conventional bomb that's laced with radioactive material.
So it's not a nuclear explosion, but it's designed to spread radioactive contamination over a wide area.
Exactly. And cobalt-60 is a particularly nasty isotope to use in a dirty bomb.
What makes cobalt-60 so dangerous?
It's a powerful gamma emitter, which means it gives off high-energy radiation that can penetrate deep into the body.
And gamma radiation can cause all sorts of health problems, right?
It can. Radiation sickness, cancer, genetic damage, you name it.
It's a pretty horrific thought that someone would even consider using a weapon like that.
It is. But it's a reminder of the destructive potential of nuclear technology.
Okay, let's move on to something a bit less terrifying. Kean talks about the Cold War rivalry between the U.S. and the Soviet Union and how this competition played out in the quest to discover new elements.
Oh, the Cold War was a fascinating time for science. There was this intense competition between the two superpowers, each trying to outdo the other in every field, including element discovery.
So it was like an elemental arms race.
It was. The U.S., with its more advanced facilities, had a bit of an edge early on. They discovered a whole bunch of new elements, including americium, curium, berkelium, californium.
Oh, I see what they did there, naming elements after American places and people.
Exactly. It was a way of asserting their dominance in the field.
And what about the Soviets? Did they discover any new elements?
They did. They discovered elements like rutherfordium and dubdium, named after the physicist Ernest Rutherford, and the city of Dubna, where their main nuclear research facility was located.
So it was a back-and-forth battle for scientific supremacy.
It was. And it wasn't always a fair fight. Soviet scientists were often under intense pressure to produce results, and they sometimes exaggerated or even fabricated their discoveries.
So even in the world of science, politics could sometimes get in the way of the truth.
It could. And it highlights the importance of scientific integrity and the need for independent verification of results.
Now, Kean also delves into the story of Viktor Ninov, a physicist who was involved in a number of element discoveries, but then became embroiled in controversy. What happened there?
Ninov was a brilliant experimentalist. He was part of the team that discovered elements 110, 111, and 112 at a lab in Germany. But then he moved to Berkeley lab, and things took a turn for the worse.
What went wrong?
Well, Ninov claimed to have discovered element 118. It would have been a huge discovery, but when other scientists tried to replicate his results, they couldn't.
So something wasn't right.
It turned out that Ninov had fabricated data. He had essentially made up the evidence for element 118.
Wow, talk about a fall from grace.
It was a huge scandal, and it shook the scientific community to its core.
It's a reminder that even in a field that's supposed to be all about objectivity and truth, there can be instances of dishonesty and fraud.
It's a sad reality, but it's important to remember that these cases are relatively rare. The vast majority of scientists are committed to upholding the highest standards of integrity.
Okay, good to know. Now let's talk about element 43, technetium. Kean points out that it has a particularly unusual story. It was the first artificially produced element.
Technetium is a fascinating element. It's the lightest element that has no stable isotopes. That means that all of its isotopes are radioactive and decay over time.
So you won't find technetium just lying around in nature.
Not really. There are trace amounts of it produced in certain nuclear reactions, but for the most part, it has to be synthesized.
So scientists actually created an element that doesn't exist naturally on Earth.
They did, and it was a major achievement. It showed that we could manipulate the building blocks of matter and create new elements that had never existed before.
It's like alchemy in the modern age.
It is. We've come a long way from the days when alchemists were trying to turn lead into gold.
So how do they create technetium?
They bombarded molybdenum, element 42, with deuterons, which are essentially heavy hydrogen nuclei.
And that transformed molybdenum into technetium.
It did, and it opened up a whole new field of research, the creation of artificial elements.
Wow, so we're not just discovering elements anymore, we're creating them.
Exactly. And it's led to the discovery of a whole host of new elements, many of which have important applications in medicine, industry, and scientific research.
It seems like the periodic table is constantly expanding.
It is, and it's a testament to human ingenuity and our relentless pursuit of knowledge and understanding. It took a while for the scientific community to catch up, but eventually they realized that Phajans had indeed made the discovery first. It's a reminder that sometimes recognition can be slow in coming, even in the world of science.
And that reminds me of that old saying, science progresses one funeral at a time.
Yeah, I can see how that applies sometimes.
Yeah.
People can get attached to their ideas.
Okay, let's talk about gold for a second. It's the element that has captivated humanity for centuries. Kean suggests that King Midas's legendary golden touch might have a more practical, less magical explanation.
Oh yeah, that's a fun one. He suggests that the golden touch could have been the result of zinc contamination.
Zinc. But zinc isn't gold. How does that explain the myth?
Well, certain zinc alloys, like brass, can have a golden sheen. And in ancient times, these alloys were highly prized. It's possible that Midas was simply surrounded by objects made from these shiny zinc alloys, which gave rise to the myths of his golden touch.
So not magic, just metallurgy.
Exactly. It's a great example of how science can help us reinterpret ancient myths and legends.
Speaking of misinterpretations, Kean also tells the story of the Fool's Gold Rush in Australia.
Oh, that was a classic. Poor miners. They were unknowingly discarding a valuable mineral that contained both gold and tellurium.
Tellurium. What's that?
It's a metalloid, kind of a hybrid between a metal and a non-metal, and it often occurs in combination with gold. But the miners didn't know that back then.
So they were literally throwing away gold.
They were. They thought the tellurium gold ore was worthless. Some of them even used it to make cement for their homes.
Oh, no. Talk about a missed opportunity.
It was a huge facepalm moment when they finally figured out what they'd been doing.
It's a good lesson about the importance of knowing your elements. Now, we've talked about gold, but Kean also dives into the history of paper money and how elements are used to prevent counterfeiting.
Yeah, you wouldn't think that the periodic table has much to do with money, but it does.
So how do elements help prevent counterfeiting? Are we talking about invisible inks or something?
That's one method, but there are others too. One common technique is to embed security strips made from metallic elements into the paper. These strips are very difficult to replicate and can be easily detected using specialized scanners.
So it's like a little bit of chemistry is protecting our wallets.
Exactly. And those security features are constantly evolving as counterfeiters become more sophisticated.
So it's an ongoing battle between the good guys and the bad guys, but at the atomic level. Speaking of battles, Kean tells the story of Charles Martin Hall and his quest to produce aluminum.
Oh, yes. Hall's story is one of those classic tales of scientific discovery and innovation. Back in the 19th century, aluminum was considered a precious metal, more valuable than gold.
Wow, aluminum, more valuable than gold. That's hard to imagine.
I know, right? But it was so difficult to extract from its ore, that is, until Hall came along.
So what did he do?
Well, he was just a young guy, fresh out of college, when he figured out a way to produce aluminum cheaply using electrolysis.
So he basically made aluminum affordable for the masses.
Exactly. His discovery led to a dramatic drop in the price of aluminum, making it the versatile metal we know and love today.
It's amazing how a single discovery can have such a ripple effect on the world. Now, Kean points out that many elements are named after figures from Greek and Roman mythology, which reflects the historical connection between science and the humanities.
Right, like titanium, named after the titans of Greek mythology, or promethium, named after Prometheus, who stole fire from the gods.
It's like a fusion of science and storytelling.
It is, and it shows how science has always been influenced by culture and the human imagination.
And Kean talks about Johann Wolfgang von Goethe, the famous German writer who also had a keen interest in science.
Oh, Goethe was a fascinating character, a true polymath. He made some important contributions to the study of optics and color theory, but he also had some pretty unconventional ideas.
Like his theory of colors, which challenged Newton's ideas.
Right, and he was a big proponent of holistic science, which emphasized intuition and observation over rigorous experimentation.
So, not all of his scientific ideas stood the test of time.
Not really, but they're still fascinating to explore, especially from a historical perspective.
And speaking of historical perspectives, Kean also tells the story of Johann Wolfgang Dobereiner, a chemist who made some early attempts to classify the elements.
Dobereiner's work laid some of the groundwork for the development of the periodic table as we know it. He noticed that certain groups of elements had similar properties and arranged them into triads.
Triads, like a musical group.
Well, sort of. He grouped elements into sets of three based on their atomic weights and chemical properties, and these triads pointed to some underlying order in the world of elements, even though he didn't have the full picture yet.
It's amazing how these early pioneers were able to glimpse those patterns, even without all the tools and knowledge we have today.
It is. It shows the power of observation and the human drive to find order in the chaos of the natural world.
Now, Kean takes us on a bit of a detour into the world of fountain pens, which seems a bit unusual for a book about elements.
It might seem like a strange topic, but Kean uses it to explore the concept of planned obsolescence.
Planned obsolescence. That's the idea that companies intentionally design products to break down or become outdated so that people have to buy new ones, right?
Exactly. And the fountain pen, especially the iconic Parker 51, became a symbol of this practice.
So these beautifully designed, seemingly durable pens were actually designed to fail.
In a way, yes. It was a way for companies to ensure repeat business. And it reflects a broader trend in our consumer culture, where disposability often trumps durability.
It's a pretty cynical strategy, and it seems counter to the idea of progress, where things are supposed to get better and last longer.
It is, but it's a reality of the modern world. And it raises some important questions about sustainability and our relationship with the things we consume.
And speaking of consumption, Kean also talks about Mark Twain and his rather ambivalent relationship with the typewriter.
Oh, yes. Twain was an early adopter of the typewriter, but also complained about it being too tearing on the mind.
So a love-hate relationship with technology. I think we can all relate to that.
Absolutely. It's a reminder that even the most brilliant minds can be resistant to change, especially when it comes to the tools they use for their craft.
Now, we've talked about elements being used in warfare, but Kean also explores their use in medicine, particularly those elements that emit radiation.
That's right. Radiation can be incredibly dangerous, but it can also be harnessed for good. Take technetium-99 meters, for example. It's a radioactive isotope that's widely used in medical imaging.
So we're injecting radioactive material into people. That sounds a bit risky.
It is, but the benefits outweigh the risks. Technetium-99 emits gamma rays, which can be detected by special cameras, and it has a relatively short half-life, so it decays away quickly.
This is like a temporary tracer that allows doctors to see what's going on inside the body.
Exactly. It's used to diagnose a wide range of conditions, from heart disease to cancer.
It's another example of how elements can be both harmful and helpful, depending on how we use them.
It is.
Yeah.
And it highlights the ingenuity of scientists in finding ways to harness the power of these elements for the benefit of humanity.
Well, we've covered a lot of ground in this deep dive into the world of elements. From the Big Bang to the heart of stars to the depths of our own planet, the elements are everywhere and in everything.
It's been quite a journey. Kean's The Disappearing Spoon is a testament to the enduring power of scientific curiosity and the interconnectedness of everything in the universe.
And it reminds us that the periodic table isn't just a chart on a classroom wall, but a gateway to understanding the very fabric of reality.
Absolutely. It's a storybook, a history book, a philosophical treatise, and a window into the future, all rolled into one.
And as we've learned, the journey of exploration is far from over. What other secrets are hidden within the vast and intricate world of the elements? What new discoveries await us in the unexplored corners of the periodic table and beyond? Only time will tell, but one thing is for sure. The elements will continue to surprise us with their beauty, their power, and their infinite potential.